All right, time for some pie, some energy pie. So you can, I don't know, did you read all the directions? Designate your choice of system with a dotted line. So for us, our system is just like the thing that we're making the energy diagrams for. Plus, we also want to be respectful of the fact that if something is changing its height, then the Earth needs to be in our system too, because of gravitational potential energy. So I'm not going to fuss at you about that. Carefully label the pies, correspond with positions, remember the 3 energy questions, and so I think that's good. So basically what I want you to do here is make some pie charts. So here, just one pie for this one little wind-up bunny. The wind-up toy is fully wound and at rest. So it's at rest. That means there's no velocity, which means there's no elastic potential energy. No kinetic energy is what I meant to say there. It's all elastic, right? There's no change in height. So that's all there. Now here, you might be asking, well, what if this was like a table and it could like fall off the end here? Would we put gravitational potential energy? The answer for us is going to be that unless something is changing height, which it often will be for us, then we're not going to worry about putting gravitational potential energy in. We're only interested if the gravitational potential energy changes. Okay, so here, there's 2 ways you could do this one, whether you're going to think about dissipated energy or not. Really, in the real world, energy is always being dissipated. And here, I'm going to do this one without dissipated energy. There's some other ones where we have to take into account for dissipated energy, I think. But for right now, I'm going to try to keep things as simple as possible. The little arrows here show us that the toy is speeding up. So when I make my little pies, one for each bunny gets its own little pie. We're going to start with a small slice of kinetic energy, and then that's going to get bigger as it gets faster. I'm kind of thinking about it like it's divided up into 8 slices, like a Domino's pizza, and each time we get a little bit more kinetic energy. So the EK part of the pie is getting bigger. So what's getting smaller? Well, there's a spring. The spring that was storing all the energy there is kind of unwinding. So all the energy that was stored in the spring is it's transforming into that kinetic energy, right? That's how the toy was designed. That's what it's supposed to do. Now, exactly how big these are relative to each other is up to you. This is a qualitative exercise, right? No numbers. So as long as your EK slice is getting bigger and the EE slice is getting smaller, that's fine. If you included a dissipated energy slice that was getting bigger, that would also be fine. I just left that out to keep things a little bit simpler for now. The toys wound up and moving up at a constant speed. Okay, so that means we know that if this right here, if we start at height 0, and that's what we're always going to do, we're going to assume that the lowest point is just the 0 height. So right here for that first pie, it is not going to have any gravitational potential energy, but it's going to acquire a little bit here, and then a little bit more, and then a little bit more, and then a little bit more. So that's going to be like no EG here. If you make your pies big enough, you can write these in there or do it with arrows like this. Doesn't make any difference to me. What about the kinetic energy? Well, it's going the same speed. So however big we decide to make the kinetic energy slice, it's going to have to be the same size all the time. So I think I will make it to be a quarter of the pie. It can't be bigger than half because That's all we have here. So I'm going to make my EK a quarter of the pi. So quarter, not a quarter of what's left. It's got to be like an actual quarter of the pi. Okay? Now what's the remaining part of it? Well, it's still a wind-up toy, right? So there's still elastic energy, the spring, and that should be getting smaller, right? And it is. Could you include dissipated energy in this one? You could. It would make it a little more complicated, but you could have the dissipated slice, if you are going to include that, has to be getting bigger. Energy's always, if energy is being dissipated, then it's going to continue to be dissipated, and that slice will keep getting bigger and bigger as you go. All right, so something like that. Here we got the toy is wound up and moving along at a constant speed, so kind of like number 3, except there's no, we don't need to deal with gravitational potential energy because it's staying at the same level. So let's see what that might look like. So how much of it do you want to make kinetic energy? Whatever we choose, we just need that to be the same for all the pi's. So I'll go with a quarter again. Doesn't matter what if you chose half or something else, that's fine, as long as you keep it the same. Okay, now what else is going on? The spring that's moving this thing along, that it has to be winding out, right? So this slice of spring energy has to be getting smaller. So maybe it was the whole thing here, like the rest of the 3/4 of the pi, and then maybe it's getting smaller. Let's make it get smaller by about 1/8 of a pi each time. Like that. And then what is this other slice that's getting bigger? Well, it's not going up a hill. So in this one, for the first time for these examples here, we're forced to include dissipated energy. Like really energy is dissipated in all these examples, but we're trying to keep it as simple as we can. So this would be our dissipated energy. So how is this one different that we had to include this? Well, it's not possible for this to happen, for it to move at a constant speed with a little spring that's wound up without some energy being dissipated. It would be, if there was no dissipated energy, then as the spring wound out, that would cause it to accelerate. That's what energy changes the situation, changes the motion of things. So that's what the spring would do. So if it's going at a constant speed, that means there has to be dissipated energy. You cannot get away from it there. All right, number 5. We're going up the hill again, but this time we are slowing down. So you probably kind of figured out the way that I like to do this. I like to do whatever pi slices are like very clear what's happening. So here, like it's very clear to me that since the velocity is decreasing, I need slices of kinetic energy that are getting smaller. So I think I will go with, how about 3/4 of it here, and I'll go down by a pizza slice per pi. Again, it doesn't matter to me exactly how much yours go down as long as the EK slice is getting smaller to reflect the fact that it's slowing down. Okay, what is this other slice, or what is the other slice? Could be made up of more than one thing. Well, we got a choice here again. Well, actually, it has to be, since we're changing height from here to here, we have to have a gravitational slice that's getting bigger, but also clearly there's this spring that's winding out. So I think this is what I'm going to do. I'm going to say that here, this is the lowest the bunny is, so I will have no EG in this one, but then I'm going to be picking up a little bit more as we go up. Let's see if I can do this in a way that will make sense. So what I need is I need EG to get bigger and EE to get smaller. So going to be all elastic energy here, and now that elastic energy needs to be getting a little bit smaller. So I'm making it by that's like a half a pizza slice. I guess that's like a pizza slice, and I should have left more room in this first one for the EE, but I think I can do it. So I'm trying to make a little slice here. Let's say when it gets to the top, the spring is all the way wound out. Or maybe there's just a tiny bit left. Either way would be fine. Okay, so that's my EE. And then the other part is the gravitational potential energy. Since this is where it starts, we're going to say that's like 0 level, so it doesn't have any yet. But now it's getting higher. So it's got gravitational potential energy and higher. Are those getting bigger? Yes. So that works. But the keys here are not that your pies look exactly like mine, but that they have the following characteristics. You need to have an EK slice that is getting smaller. You need to have an EE slice that's getting smaller. And you need to have an EG slice that is going from none to getting bigger. It has to have those characteristics. It's possible to do this one with dissipated energy in there as well, but obviously that's going to make it even more complicated. So dodge that one. All right, so our last one here. Toys wound up and speeding up as it moves up the incline. So same as this going up, going to have the increasing slice of EG, but our kinetic energy is also increasing. So I'll have to think about how to achieve that. So what's going on? How is this toy different from this one? This one has a stronger spring in it, I guess. So maybe at the beginning, when it's just barely moving, we'll say it's got like a tiny slice of EK, and the rest of it, this is like the 0 height, so there's no gravitational potential energy yet, so all of this energy is stored in the spring. Okay, now EK is going to get bigger, and now there's also some gravitational potential energy, so EK and EG, and the rest must be that elastic energy. And then both of these get bigger. Those look bigger, right? And the EE is winding out. Maybe I could have made those a little bigger, and that doesn't look like it changed that much, but that's fine. Then maybe like this, and then maybe like this. So again, it's not important that yours look exactly the same as mine. What's important is that you have the following features: that the elastic energy, the little elastic in the bunny, is winding out, so that needs to be getting smaller. The EK, since the bunny is speeding up, needs to be getting bigger. And since the bunny is going up the ramp, the EG needs to go from none to getting bigger. And that's some energy pies for you. That's how you do it.